Hi everyone, my name is Tasaki. I'm a mathematical physicist. In this webinar, I like to discuss two number-theoretic theorems and their elementary proofs. But before going on, I'd like to warn you that until very recently, I didn't know almost anything about the number theory beyond what I learned in high school. And my knowledge is still very, very poor. So if you're looking for a good lecture video by an expert in number theory, then I think you should stop watching this right now. Okay, see you. And anyway, here I discussed two number-theoretic theorems that we found useful in quantum physics. So here's the background. Very recently, my friend Naoto Shiraishi and myself wrote a paper on a simple rigorous example of thermalization in an isolated macroscopic quantum system. I'm not going to discuss what this is, but in this paper, we made use of two number-theoretic statements, and we used this to discuss the spectrum of something called a free fermion chain. And anyway, they were very useful, and we completed this work. But I was also interested in these theorems, and I wanted to learn how people can prove such interesting theorems. And I won't say that I learned some number theory, but by going through references, I at least learned how to prove these theorems. And so that's why I recorded webinars. So I will explain here in a very elementary manner how you can prove this. And I must thank Shin Nakano, who is my colleague and who is an expert in number theory. I won't say I learned number theory, but anyway, everything about number theory I know is from Shin. And he carefully instructed me what I should learn, what I should read, and so on. So without him, I was never able to complete this work. And also, I was not able to record this webinar. But I tell you that Shin is not responsible for this webinar. He didn't supervise. I just made this by myself. Okay, so if you find anything inappropriate, he is not responsible. Okay, so anyway, let's get started. So here are main theorems that I want to discuss. So let P be an odd prime, like 5, 13 or something. And let theta be the piece root of unity. Which is written like this, and it satisfies this. And here's the statement, very interesting statement, and this is well known, and that this follows from famous theorem by Gauss. So here are rational coefficients, and I assume that not all of them are zero. And then the theorem said that this linear combination is non-zero. So this means that the combination of them are linearly independent when the coefficients are rational. And here are very important remarks. First of all, it is essential that P is a prime. So consider this case P is 4, which is not a prime. And then theta is I, and this is -1, and this is -I. And in this case, you find that theta plus theta cubed is 0. So this theorem does not hold. And so, of course, so it's essential that P is a prime. And also, I think this is clear, but okay, one never has linear independence if these coefficients are real. Okay, and of course, this is P equal 5 case. It's a prime, but anyway, these are just two-dimensional vectors. So if the coefficients are real, then of course they are not linearly independent. Or at most, two vectors can be linearly independent in 2 dimensions, right? So this tells you that the word of real coefficient and real and rational coefficients are very, very different. And isn't it interesting? So as I said, I didn't know any number theory. So I found this very interesting when I first learned about this. And as a simple corollary, this is what we used in our quantum physics paper. But as a corollary, you find that if these are integer coefficients, and if not all of them are 0, then this linear combination is non-zero. And of course, this corollary follows from this immediately. But if you think a little bit, you find that these are actually equivalent. Okay. Anyway, so this is the corollary that we use. But we also wanted a lower bound. So this sounds that this is non-zero. But we also wanted an explicit lower bound for the absolute value of this. And this is one one lower bound. And I learned this lower bound from Wataru Kai and Kazuaki Miyatani. And as I said, this one is very, very standard, and you can find in many, many textbooks, but we didn't find this lower bound in the literature. So we learned this from them. And how did it go? Actually, I knew that if we have some lower bound here, then we can prove something about the free fermion chain. So I posted a question to Twitter, and if I asked if anybody knows some lower, but non-trivial lower bound for this quantity. Then immediately, within the same day, within several hours, Wataru and Kazuaki independently posted very short post to Twitter. And this contains the statement and the proof and everything, okay? And so for them, it didn't take one day. But anyway, we learned this, okay? And so in this webinar, I'd like to discuss elementary proof that I understood about this first theorem and this second theorem. Okay. Okay, let me start from the proof of theorem 1, which is this linear independence of these thetas. Okay. Then the essential 2 is a formal polynomial in T. Okay, when I say formal polynomial in T, we don't say that we don't specify T is real, variable, or complex variable, but we just consider formal polynomial. I think you know what this is. And anyway, let's consider this simple polynomial, T to the P minus 1, and then you can factorize this like this, where Ft is this. And this is known as the cyclotomic polynomial. And you know that this theta, the pth root of unity, satisfies this, but it's not 1. So you find that this satisfies this. So if you here, you substitute theta for t, and then you get this. So that's the reason that we are interested in this cyclotomic polynomial. And here's the important lemma, which is due to Gauss. Okay, and it says Ft is irreducible. More precisely, it says that Ft cannot be factorized within polynomials over Q, rational coefficients. So to be more specific, this is a statement. You can never write Ft like this, where Q and R are at least 1, and all these coefficients are rational. Okay, so this is what we are going to prove here. But before proving this, this makes the job easier. So yeah, this is what we wanted to prove, but it suffices, for this purpose, it suffices to show that we never have this for integer coefficients. And why? Well, this is again due to Gauss, and here's the statement. So suppose that we had this with this rational coefficients. Okay, then there always is a big enough integer n, and if you multiply everything by n, and then all of them becomes integer. Okay, and then you divide both hand side by n, but you factorize n into primes. Again, then we claim that for each prime factor pj, it is true that pj divides all of these b, or all of these c. Okay, and actually I'm not going to prove this. Sorry, I think this is the only part I cheat. You can easily prove this by assuming the converse, and then you work a little bit and you find a contradiction. Okay, it's not very fun, so let me skip this part. But anyway, this is a very famous trick by Gauss. So if you look at most of textbook number theory, you find this trick. So anyway, so this fact tells you that we again have this with integer coefficients b and c's. So this proves this claim. Okay, so now we want to prove the irreducibility of f, but we know that we only have to consider polynomials over z. Okay, so this is the cyclotomic polynomial that we want to prove its irreducibility. And now I substitute s plus 1 to t. S is again a formal variable, okay? And of course, it becomes like this. And then you can expand this like this. And here, now you can write this coefficient explicitly using this binomial coefficient. And in particular, this the highest power is p to the p minus 1, and the coefficient is 1. And the lowest coefficient is p, and all other coefficients are divisible by p. This is very important. So fs plus 1 looks like this. Okay, because of this, this is s to the p minus 1, and here is p. And you assume that this is factorized like this with q and r at least 1. Okay, and now since this highest power is s to the p minus 1, here you have to have this with an integer coefficient. And here you have this p, and the p is a prime. So one of them must be p, and one of them must be 1. But let's assume that this has p, and this has 1. So let's write this as this, and this as this. Oh, and I also write this formally as this. Okay. Now, after defining this b, I let L to be something between which is larger than 1 and less than equal to q, such that all b0, b1, bl minus 1 are divisible by p, but bl is not divisible. Okay, and I claim that such L always exists because, first of all, b0 is equal to p, so it's divisible by p. Okay, and also you find that I didn't write it, but here bq is 1. So since bq is 1, it's not divisible by p. Okay, so this guarantees that there is such L. Okay, then recall that A is defined like this, so I compute AL, and it's of course written like this. And if you write it more explicitly, it can be written like this. But as I said, all these, because of this assumption, they are just divisible by P. And now note that recall that C0 is 1, and I assume that BL is not divisible by P. So this AL is not divisible by P. Okay, but this is a contradiction because we know this. We know this. Okay, and of course, this L must be less than equal to P minus 2. Okay, so this contradicts with this fact. Okay. So this is very elementary, but this is very powerful. So we are done with the proof of irreducibility. Okay, and this trick is actually it's very well known, and it's called. I'm sure that most of you, if you are from physics, you might have thought that Albert Einstein is so clever that he has a contribution to number theory. He is clever, but this is not Einstein. This is Eisenstein. Okay. All right. So we are done with this irreducibility. So we can now proceed to the proof of this statement. Okay. So we want to prove that this thing is non-zero. So I again define a formal polynomial in T like this, using these coefficients. Now I note that the degree of this polynomial G is at most P minus 1, and the degree of F is P. So this is strictly larger than this. Okay. By using this fact and the irreducibility of Ft, you can prove that there are polynomials over Q, A, B, such that AF plus BG is equal to 1. Okay, I'm going to prove this in an elementary manner. And then you substitute theta into T here, and recalling that F theta is 0, so this becomes 0, and you end up showing B theta, G theta is 1. And so this implies that G of the theta is non-zero, of course. And this is what we wanted, but this is equal to theta times G theta, and this is non-zero. Okay, so that is the proof of this statement. So we only need to prove this star. To prove this, we use something known as the Euclidean algorithm. I think you learned this in high school, that it's a method for obtaining the greatest common divisor of two numbers. Okay, but this is a polynomial version, but the essence is the same. So we are interested in these two polynomials f and g. So let me write this as f1, and let me write this as f2. Okay, also these are the polynomials. And then since this F1 has higher degree than F2, you can sort of divide F1 by F2. And here's the quotient, and here's the remainder. If you don't recall what this is, here's an example. So if F1 is this and F2 is this, and then you can also, here's how, I don't know where I learned this, but I found that I knew how to do this division. So probably I learned this in high school. So here's F1, and here you write F2 here, and this is how, probably you have different way of computing, but anyway, I did this. And so you got this quotient, and this is the remainder. So it's like this, okay? So let's go back to the general. So so we do this division of polynomials like this. So everything is polynomial in T, okay? And the degree, and here's the inequality between the degrees. And now, this is actually the essence of the Euclidean algorithm, and this is the same for the case of numbers that you know. And if D is a common factor of F1 and F2, and then if you look at this relation carefully, you find that D is also a common factor of F2 and F3. Okay, and you can also repeat this many times. So actually, if you set j equal 1 here, you get this. But you can have the same, you can do the same thing with j equal 2 and so on. And you repeat this several times until your remainder is 0. And then you stop this algorithm here. And the final thing you got was fk. Okay. And now, from this consideration, you find that fk is a common factor of fk minus 1 and fk. And then from this, with different indices, you find that this fk is actually a common factor of all of these f's. And so in particular, it's a factor of f1. But I recall that f1 equal f is irreducible. So it cannot have a non-trivial factor. Its factor must be a number, which is a rational number. So if k equals c. Good. Now, recall that here we have a recursion relation for defining f of j. Okay, so here's the relation. And now I bring it here and slightly shift the index. And so that to write down this recursion relation for going in the opposite direction. Okay, and if you use this, and if you start from fk, this is the final thing that I've obtained. You can express fk in terms of fk minus 2 and fk minus 1, and again use this. You can express this in terms of this, and so on. So you repeat this until you only get f1 and f2. And this A tilde and B tilde are written by simply multiplying and adding these Q1s. Okay. And we recall that fk is just a rational number. So this is equal to c. Okay, this is equal to c. And so you define A as A tilde divided by C and B as B tilde divided by C. And then this reduces to this. And of course, A and B are just polynomials in T. So we proved what we wanted. Okay. And of course, I always tell my students to work out examples. So I did. So this is a simple example. But if this F is this and G is this, I already discussed this. You have this. Then so you define F3 as this remainder, and you divide this F2 by F3 to get this is a quotient, and this is the remainder, and you do the same thing again. And this is F5, but you find that F5 is just a number. F5 is just a number. And now you want to express F5 in terms of F1 and F2. So you use this recursion relation I think twice or 3 times to get this. Okay, so everything, these are written in terms of just Q's and 1. Okay, and now this leads to AF plus BG equal 1, where A is 1 over F5 times this, and B is 1 over F5 times this. Okay, so these are A and B, and we get this relation, This is just an example. Okay, so I'm done with theorem 1. Let's proceed to the proof of theorem number 2. Okay, so here's the notation. This Q of theta, this is actually a field. It consists of this kind of complex numbers. Okay, so these are rational numbers. And z of theta is very similar, but it consists of this kind of complex numbers with these integer coefficients. Okay, and first of all, I discussed the notion of conjugates. This is, of course, very standard in the theory of field. And so we consider this sequence. Theta j is something between 1 and p minus 1. It's an integer between 1 and p minus 1. And consider this sequence. And I claim that this is a permutation of this. Okay. Here's a simple example. Let p be 5. And then this is, and let j be 3. And this is j to the third, j to the sixth, j to the ninth. No, theta. I'm sorry, theta to the third, theta to the sixth, and okay. But since theta to the fifth is 1, you see this is this, and this becomes this, it becomes this. So this is just a permutation of this. And of course, a proof is just immediate, very easy if you find this. Okay, so you have this fact. Of course, it's essential that P is a prime. Okay, and now you take alpha, an element of Q to the theta. So it's this, and these are rational coefficients. And then for each j, we define the conjugate of alpha by this. Okay, so it's basically the same, but theta to the n is replaced by theta to the n, theta to nj. Okay, so this is a permutation of this thing. But so again, you get an element of this. And by definition, you easily find that this addition splits like this. And if you have this multiplication, it goes like this. Okay. All right. So this is the definition of conjugates. And here's, again, the standard notion called the field norm. Field is, of course, not the field theory in physics, field in the algebra. And for any element in Q of theta, we define its norm. So this is very different, I think, very different from the norm that we meet in analysis and so on, but in quantum mechanics. But anyway, so this is the definition. You just multiply all these conjugates. Okay, and here's the essential lemma that we use in the proof of the theorem 2. Okay. For any, if alpha is an element of this, so if the coefficients are all integers, then this n alpha, the norm, is an integer. Okay, and here's a proof for an expert, not for me and probably not for you. In general, you know that from the general theory of field that this takes a rational, that the norm is a rational number. Okay, and this alpha happens to be something called an algebraic integer. And n alpha is also, this means that n alpha is also an algebraic integer. But it's well known that an algebraic integer that is rational, it must be an integer. So QED. But of course, this does not, I'm sure that this does not make sense to most of you. And I will give again, standard but elementary proof, which only uses very elementary linear algebra. Okay. But anyway, so we have this lemma. So let's prove theorem 2 by assuming lemma. Okay. So here is our alpha, which is the element of this. And its conjugate is by definition this. Okay, so now let's observe that. Let's make a simple observation. If you take the complex conjugate of this, and then since theta is e to something, e to the I, p over 2 pi, you see that this complex conjugate is the same as this inverse. Okay, and since theta np is 1, you can rewrite it like this. But then you find that this, if you compare this and this, you find that this is equal to sigma p minus j of alpha. Okay, so here's the product. But so there are even number of terms in this product, but you find that this guy and this guy are complex conjugates of each other. These guys and this guy and these guys, they are complex conjugates of each other. So you can only consider half of this product and just have this absolute value squared. Okay, and you also recall that sigma 1 alpha is nothing but alpha, so you pull it out. So it's alpha absolute value squared. So this is like this. And you immediately see that it's greater than or equal to 0. It's non-negative. Okay. Now, here's an essential step. So from theorem 1, and the fact that this is just a permutation of theta to the n, you find that this has a precise form that theorem 1 applies. And you see that this is non-zero because not all of them are 0. Okay, so we know this. And so this means that this is just, the norm is simply the product of all these guys, so it's non-zero. But we know it's non-negative, so we know that it's strictly positive. Okay, it's a small piece of information. But from the lemma, we know that n alpha must be an integer. And then this abstract fact sort of boosts this inequality. This only says it's positive, but by knowing this, this is boosted into very meaningful lower bound, which says that n alpha is greater than or equal to 1. Very good. And now, so this is our expression for the norm, but this must be greater than or equal to 1. So if you bring this to here, you get this lower bound for alpha absolute value squared. Okay, and here sigma j is defined in this way. So by using the triangle inequality, you have this trivial upper bound for sigma j alpha. So by using this, you get this lower bound for alpha absolute value squared. Okay, so we are done. Okay, so the only thing we should prove is this lemma, which says that the norm of this alpha, which is in z of theta, is an integer. Okay, the proof is very interesting. And as I said, it only makes use of elementary linear algebra. And the only thing you need is what I teach in my freshman physics course in mathematics. Okay, so let me start from a simple observation. Consider theta times theta to the n. And it's, of course, theta to the power n plus 1. But when n is p minus 1, and this is, of course, theta to the pth. And because this is a pth root of unity, this can be written. This is also written in this way. Okay. So write this innocent relation in the vector form like this. You have this vector of theta from theta p minus 1, and you multiply theta. And of course, the result is this. And then you can write this in the matrix form like this. Okay. And I think it's just clear. And this matrix here is a very simple matrix, which whose entries are either 1, -1, or 0. Okay. And now you can repeat this procedure. You can further multiply theta here, and then it goes through this, of course, and you multiply this and again. And so you find this relation. Okay, the application of theta n, multiplication of this vector by theta n is equal to the multiplication of this vector by z to the power n. Z is this matrix. Good. And so we have this relation. And you apply this conjugate to each entry of this identity. And then on the left-hand side, you have this here. And on the right-hand side, z is just the coefficient, just the integer coefficient. So you have this. Okay. And so what does this say? Well, this relation says that theta, theta p minus 1 are eigenvalues of z. And they are distinct. So we have p minus 1 distinct eigenvalues, and the dimension of z is p minus 1. So this means that z is diagonalizable. And, well, you don't have to work out this explicitly, but this p is just a standard thing. You just place eigenvectors. But anyway, so you see that this matrix z can be diagonalized like this. Okay. Now you take alpha, which is an arbitrary element from Q of theta. Okay. And then you similarly consider the multiplication of this vector by alpha, and you can write it again by using a matrix A like this, and A is explicitly written in this way. So A is a matrix with rational entries. Okay. And now, by using the same P as before, if you sandwich A by P inverse P, you can diagonalize this. And because it's like this, so you have this. And since this is this, and if you recall the definition of these conjugates, you find that you precisely have conjugates here. Okay, so now you find that this is A is diagonalized like this. In this diagonal element, you have these conjugates of alpha. And from this, you immediately see that you can compute the determinant of A. Okay, if you compute the determinant of A, it's the same as this, and it's just a product of its eigenvalues. And this happens to be exactly the same as the definition of the norm. Okay, so you found this is, of course, very, very standard. So you found that the norm is equal to the determinant of this matrix representing the action of alpha onto this vector here. Okay, so now we are almost done. Okay, suppose that alpha is an element of Q of theta. And in this case, C is all rational numbers. So this means that, and Z is a simple matrix. So this means that all the entries of A is rational. And then, of course, the determinant is a rational number. So you find that this N alpha, the norm is also rational. It's the same thing. This is what we wanted to have. If alpha is the element of Z of theta, it means that C are all integers. This means that all the matrix entries of A are integer. This means that its determinant is integer, and N of alpha is an integer, QET. Okay, so this is how we prove these sort of miraculously looking theorems, theorem 1 and theorem 2. Okay, and as I said, I think the proofs were very elementary, and I found them very interesting. And so I'm happy that if you found them also interesting. Okay, so thank you very much for watching. Goodbye.